Well, good morning, folks, and thanks for being here for the New Horizons Forum this morning. It's my distinct pleasure this morning to introduce to you Dr. Werner Dahm. Dr. Dahm is the Director of the Security and Defense Systems Initiative and Foundation Professor of Aerospace and Mechanical Engineering at the Arizona State University. Previously, he served as Chief Scientist of the United States Air Force. He's a Fellow of the AIAA, and he'll speak to us this morning on establishing trust in autonomous aerosystems. Dr. Dahm.
Well, thanks, Tom, for the introduction, and thanks to all of you for coming out at 8 in the morning on what will kick off the third day of the AIAA Aerospace Sciences meeting, and I think promises an agenda that looks very good. A lot of interesting papers and talks. I understand we had a panel on autonomy as part of the meeting, and that's very closely tied to the subject of what I want to talk about here in the next kind of 45 minutes or so. As Tom pointed out, the subject here is how we go about establishing trust, and by that we mean certifiable trust in autonomous systems in general, and particular focus on Aerosystems. So the real focus here is how do you go about doing verification and validation of a set of systems that are fundamentally difficult to do that on, and I'll explain what I mean by that in just a bit. I would argue that that topic, V&V, directed at establishing certifiable trust in autonomous systems, is one of the greatest challenges that faces aerospace engineering and indeed the broader engineering community for probably the next 10 to 20 years, with the big push we have underway in expanding the implementations of autonomous systems very broadly across society. So what I'm going to do here is talk for about 45 minutes on that topic, give you my thoughts on it. I'm going to leave about 10 minutes or so at the end. I would invite you, as we go through this, those parts that you agree with, disagree with, or whatever it might be, queue up those questions, and I'll make sure we leave about 10 minutes or so at the end of this to cover those. So the title here, or the talk, really deals with autonomous aerosystems, and by that we mean primarily the set of manned and perhaps optionally manned air vehicles, some of which are shown notionally here, fixed-wing systems, VTOL systems, but also a very wide range of other kinds of systems that have substantial levels of autonomy enabled in them. And that includes things like autonomous or semi-autonomous munitions, a variety of sensor-fused systems, and really a whole host of other kinds of engineered systems where there is substantial autonomous reasoning and control involved in them. And that doesn't just have to extend to air vehicles or systems like that, but things like decision support aids. Certainly the next-gen air traffic management system I'll refer to in just a bit is an example of a highly autonomous system. Now, I'm going to use the word autonomous here pretty broadly. I'm not going to go down the rabbit hole of defining what I interpret autonomy to mean. I'm going to infer what I intended to mean by the comments that I'm going to make here in the next few minutes. But when we talk about autonomous systems, I want us all to understand here that we're not talking necessarily about fully autonomous systems where there is no longer any human operator control of the system. In fact, autonomous systems can span all the way from systems that the human operator has decided at the moment they're going to maintain complete control over, to systems that have fairly low degrees of autonomy enabled in them, and all the way up to fully autonomous systems. So the term of art that's sometimes used there is flexible autonomy, where a human operator can allow the system to take on whatever degree of autonomous control that they want it to. So broadly, these are systems where there is substantial cyber-based intelligence and autonomous control that is tightly coupled to a physical system. And the term that's being broadly used for those kinds of systems are cyber-physical systems. The intelligence that is enabled by the deep amount of processing and data storage that's resident on the system itself, that leads to the ability to have a high degree of adaptivity in the system. And then as we'll go through this, you'll see that these systems have a very large number of degrees of freedom in the way that they can operate. And that allows them to take on a very wide range of adaptations and ultimately leads to a complex adaptive cyber-physical system. So this chart shows some of the key issues, and it's just a sampling of them, key issues that are relevant to complex adaptive cyber-physical systems of this type. And they range from things like intelligent or integrated system health management to fault management. I'll have some points to make about how fault management in complex adaptive systems has to be done very differently than it has in traditional engineered systems. System reliance, making sure that these systems are not able to be rendered inoperable or poorly operable under a small number of faults. Goal-based supervisory control directed at verification and validation of the whole system operability, and then finally at certification of the system so that it can be actually used in practice. So this talk, or the subject of the talk, as I said, I believe is central to much of what the engineering world, and certainly the aerospace engineering world, is going to be facing for the next 20 years. It is all the more urgent, if you will, as a result of this recent directive that came out of DoD from Ash Carter just about 6 weeks ago that states what the DoD policy is for verification and validation of autonomous systems. So it says that the purpose of the policy as declared is to establish DoD policy and responsibilities for the development and use of autonomous and semi-autonomous, recall the term flexibly autonomous, functions, especially in weapon systems, but interpreted broadly, including manned and unmanned platforms. And then it establishes guidelines for minimizing the probability of unintended consequences of the operation of systems like that, and the probability of failures in these autonomous and semi-autonomous weapon systems. The policy is very simple, and it's got about 5 or 6 parts to it, but the key one that's relevant here is that these kinds of systems are mandated to go through a rigorous hardware and software V&V process under realistic conditions to provide the DT and OT, OT and E capability that's going to ensure that these sorts of systems are sufficiently robust so that we minimize failures of the systems, and in particular we minimize unintended or unacceptable consequences of failures of systems like that. So that's the new or formally declared. It's always been implicit, I think, in the DoD thinking on autonomous systems. That's the new, now formally declared policy. The real question is, how do you go about achieving that? As we step through this and we talk about the kinds of autonomous systems that DoD is already well into developing, you'll see that actually doing this is far more difficult than stating that in the policy might sound. Now, this topic was near the forefront of the 2010 Headquarters Air Force level report on technology horizons, which I led when I was in the Pentagon as the Air Force Chief Scientist. That report has 4 volumes, the first of which is publicly releasable. It is available on the web, and it really charts out those areas where the Air Force is going to be looking at science and technology investments to advance some key capabilities that are needed for the strategic environment, the technology environment, and the budget environment that it faces over the next 10 to 20 years. As a result of this fairly extensive study that was done, and the sections of the report are outlined there on the right-hand side, it goes all the way from a very high-level assessment of the strategic context over that 20-year time frame through a set of enduring realities that the Air Force is going to continue facing. And while it's an Air Force report, much of what it states applies broadly to other parts of the DoD and really the broader engineering community as well. And then it goes through a set of potential capability areas and identifies the key technology areas that are needed to enable each one of those areas. As a result of that process, one of the things that came out of that, and this won't surprise anyone in this room, is that there will be a greatly expanded growth in the use of autonomous systems across a whole variety of applications that the Air Force is going to be involved in. And this goes, and we use the term autonomous systems and processes because it goes well beyond the kinds of unmanned systems that we're all familiar with today. In fact, it reaches far beyond that. There are going to be dramatic increases in the range of those kinds of systems and processes where autonomous reasoning and control can be applied. These systems are going to be increasingly based on a higher degree of system self-awareness, awareness of its own health and status, if you will, of all the subsystems, awareness of the other systems that it interacts with and the environment that it's interacting in, and then the ability to adapt and adjust the system to maximize its capability under that defined state of awareness. So it turns out that the science and technology challenges that are needed to establish this certifiable trust that's required now under the DoD directive in order for us to be able to field systems like that is absolutely key to this whole area. I would contend that the engineering community's ability to conceive, design, and build and test systems like this is far beyond our ability to ensure to the DoD and to the broader public that these kinds of systems are going to actually operate the way that they're intended to and not be able, as a result of the high degree of autonomy and the adaptivity that they have, be able to take on system behaviors that are unacceptable in a variety of ways. Now, the bottom bullet is really one of the key points I want to make here, and that's that traditional fault management approaches are going to have to be substantially re-engineered to enable these kinds of flexibly autonomous systems to be certified at the level that is required in the DoD and more broadly. So on this chart, what I'm showing on the left-hand side is one example of a complex adaptive system, one that we all in this room know very well. And these are aircraft systems like fifth-generation fighters that today are deeply integrated software-driven systems. And I think we all understand that today the overwhelming majority of all the functions that a system like that does are driven to one degree or another autonomously by software that's resident in the system. And the F-35 example has shown, and I think there are many others, that the software development and validation account for the bulk of the costs of a system like that. And as the DoD moves towards things like more adaptive radars and a variety of other systems that will also have this high degree of adaptivity, I think that fundamental cost challenge and the technical challenge that creates that cost challenge are going to be central to this. The right-hand side of this chart just reminds us that what's happening in the DoD with autonomous systems is not somehow an outlier. This is happening throughout society. And I'm showing the example here. You know, the chart says premium cars, but you can go to an auto dealership and a mid-level car today has very substantial instantiations of autonomy in it. Things like auto braking, when you're approaching another car on the highway, lane drift warning, autonomous parallel parking, and a variety of other functions that are ways that the industry attracts buyers. I'm told in the auto industry it's about 70% of the development costs and about 40% of the production costs are tied in one way or another to the software systems that enable these varying levels of autonomy. Today, those systems are still pretty highly federated, and so their capability is fairly marginal, and the ability to ensure that they operate the way they're supposed to is not as challenging as it will be for future systems where the subsystems interact much, much more strongly than they do in today's systems. And if we look beyond, cars and other systems like that, the smartphones that we all know and love are complex adaptive systems, right? They adapt to the way you use them in many instances, even without you being aware that they are doing that. And we'll be doing much more of that as time goes on. At the top right, that's a picture of the Verizon Global Network Operations Center in Bedminster, New Jersey. That is a massive, autonomous, largely autonomous and adaptable system that is actually managed by a surprisingly small number of human supervisors and relies on the system itself to manage itself. At the lower left, next generation air traffic management, I mentioned before, when fully implemented is going to have various levels of autonomy represented throughout that system. And the flying public and the broader public is going to demand that that system be able to be certified that it operates in the way that it's supposed to. In the bottom center, many of you, I think most of you are aware, we are moving to a future where electrical grids are going to be smart grids that have the ability to adjust their operation, their configuration under various fault modes or various load demand modes or generation modes to be able to optimize the delivery of power across the public. And then commercial aircraft and a variety of other systems as well. So don't think only DoD here, but my comments are going to focus primarily on DoD systems. And on this chart, what I'm showing is just some examples of notional unmanned or optionally manned systems of the kind that are under development today that have high levels of adaptivity and autonomy associated with them. And just to give you an idea here, you should be thinking about platforms like this that might sustain failures of parts, actuators, control surfaces, or other subsystems as a result of either normal operations or perhaps battle damage, be able to be aware of their current health and status and then adjust the flight control system to be able to maximize the ability of that system to execute the mission that it's been given under the state that it's operating in. So that involves adaptive guidance and control with autonomous high-level reasoning systems that take in a tremendous amount of sensor information about the state of the platform, about the operating environment that the system operates in, about the health and status of other systems that it interacts with, and then makes its own decisions, or to varying levels, its own decisions about how it's going to be able to execute that mission. This chart is just a reminder of how we got here, so to speak. The very fine scale, if you will, component technologies that have made possible these highly adaptable autonomous systems. And they start with the advances over the last 30 years in miniaturization and fabrication of very small scale components, in part through things like MEMS and other fabrication technologies. The growth of sensing or ubiquitous sensing, small, cheap, and very reliable sensors, in many cases having multimodal sensing capability. The rapid spread of embedded processing, very highly capable embedded processing, so multi-core GPGPUs and other approaches with processing speeds that allow a very small subsystem to do a tremendous amount of processing of the sensor data. Along with cheap, vast terabyte scale compact storage, inexpensive solid-state storage devices, and then everything that's been happening in the software adaptation and learning community with expert systems and genetic algorithms and machine learning and whatnot. So all of those together have combined to produce or give us the ability to be able to engineer systems like this. Now, in my taxonomy, my own taxonomy, I would argue that there are four required attributes for what I would deem a highly adaptable autonomous system. And the first is, and they're shown on these four sub-bullets here, the first is that they have to make use of a large number of sensor inputs, and those may be onboard sensors of the type that we just talked about that assess or help assess the health and status of the system. They may be various off-board sensors that come from other platforms or elsewhere in the environment. So a large number of inputs into that reasoning system. Secondly, they have to make a large number of interdependent decisions based on those sensor inputs. So there's a great deal of fusion of sensor data, and then making not individual isolated decisions, but a large number of interdependent decisions. And then thirdly, the system has to be able to undergo a large number of adaptations in its current state. Those adaptations may be fully deterministic. I will argue as we go through this that more and more we want those systems to be able to have a stochastic component to the adaptations. And then finally, those adaptations themselves have to evolve continuously through a self-learning process. So the bottom line here is, as the number of inputs into the system and the number of possible system adaptations becomes very large, these essentially become near infinite state systems. And that's what drives the V&V challenge that is faced in engineering systems like that. So the points here on the left-hand side just note that in a system like this, there are many interacting what we'll call agents, right? Those agents may be subsystems, they may be parts of the decision control system that underlies this larger system. A key point is that there is no single agent on a platform like this that has a full global view of the entire system. Even the reasoning engine that is making decisions about how to adapt the system doesn't have a full view of the system. It's a decentralized structure, and no one agent has full control of all the others. Some of those agents, and there are systems where the agents are all identical. The term that people like to use for those are swarm-like systems. I think that is a niche in this broader area. I don't think it's the focus of this. I think certainly in the broader DoD and broader society at large, it is systems where the individual agents may all be different, or at least where there's substantial differences among them, and where they're not individually simple. So we know from looking at research on systems like this, where there are a large number of independent agents, that there is the potential for emergent behavior, high-level system behavior that's driven by the dynamics of the interactions among all of these individual agents. And a key point here is, and we've seen this in even very simple system studies, that the high-level system behavior typically cannot be, certainly not fully inferred, and it can't in many cases even be anticipated from the behaviors of the individual agents. It really is an emergent kind of behavior, and that is what creates the potential for these systems, as they become more highly adaptive and autonomous, to take on system behaviors that the designer never had intended, and then indeed that we might find unacceptable. So on this chart, we're just talking about the state awareness and how the system self-adapts to that. We mentioned earlier that self-awareness could have to do with the system health. It could have to do with the operating environment that the system is in. More and more, I believe these systems are going to be self-experimenting to try to determine what their state is. They may be dithering control surfaces to determine the functionality that's remaining in them, and then feeding that information into a high-level reasoning engine. We'll come in just a second to talk about goal-based control, control of a system that has this ability to adjust its own operation can no longer be articulated to the system in a very precise task-level statement. The control has to be expressed at a goal level, and then the system is responsible for determining how to achieve those goals based on its current state. Now, the next to the last bullet is very important. Once you go through this, this eliminates the possibility of you as a designer anticipating what all the possible failure modes of a system like that are, and then following the traditional fault management paradigm for each of those anticipated failure modes, you then conceiving what the appropriate response of the system is. Instead, we're going to have to allow the system to determine what its current abilities are, and then adjust itself to be able to achieve those high-level goals that we talked about. So the adaptation here goes, we said, from human-driven to fully autonomous. That's this flexible autonomy concept. The system on its own seeks the best course of action. It doesn't rely on a set of pre-planned options that you as a designer have given it. and the operator interacts with that system really at that very high level. Now on this chart, what I want to do is begin to distinguish between the traditional fault management paradigm that we've used to engineer systems for the last, well, really almost from the start of what we would call engineered systems, but certainly in a big way since the advent of the space program, where we went to systems that had a far higher level of complexity than was the case before. And traditional fault management is based on the detection, the isolation, the identification and characterization of a discrete set of anticipated faults, and it envisions the system operating in a nominal state that might occasionally be punctuated by occurrences of these anticipatable predefined faults. And then the fault manager goes about anticipating those faults and determining what the appropriate set of responses to every one of those faults is. And that's worked well historically when systems are sufficiently simple, that is to say when they have a low degree of adaptivity associated with them. But as the system complexity grows, so does the number of possible faults, and in fact the number of possible faults can then grow so large that for all intents and purposes you cannot possibly anticipate all of the faults, and as that set becomes very large you can only anticipate a vanishingly small subset of those faults. And in that case, this almost turns on its head, where your desire to go down the traditional fault management path may drive you to tell the system to do something that is in fact fundamentally poorly suited to the fault state that it's currently in. So in these highly adaptable systems, a fault is now no longer the way we understood it in traditional engineered systems. It's not something that can be anticipated. And it's not something that we engineer a direct solution for. And as the number of possible faults goes up, there's a much greater likelihood of you having multi-fault interactions and fault management failures. So as the systems become increasingly complex, we find ourselves where the system is continually in a fault mode, and I'll show that on the next chart. But in effect, because the system is constantly adapting, we then understand a fault to be not something that went horribly wrong in the system, not in the traditional way, but something that requires the system now to adapt on this next cycle. So the idea of a fault now can be something that may be quite benign, but that causes the system to have to change its operating state into a new one. And it's that ability of the system, essentially no matter what you throw at it, either in terms of the operating environment or its current health and status, no matter what you throw at it, the ability of the system on its own to adjust to that, that's what provides the inherent resilience that we're trying to get systems like this to achieve. So on this chart, what I'm showing on the top are kind of a notional sketch at the top right of what a traditional simple engineered system, how it interprets nominal operations shown in the green and sort of in a Venn diagram sense, the much smaller set of discrete faults and where those overlap, that's the set of faults that we try to detect and localize, identify, characterize, and then have pre-scripted responses for. In the bottom is a cartoon that shows what these complex adaptive systems are going to be operating in. So where the green and the red spaces now overlap much, much more broadly, the concept of a nominal operation that's occasionally punctuated by a discrete set of faults doesn't really apply anymore. And the appropriate goal level of response that the system depends on is something that it has to come up with on its own. So a very different kind of fault management paradigm. So here in the first bullet, these near infinite set of possible faults that exist in these complex adaptive systems make traditional fault management not only largely impossible, but as I'll argue at the bottom of this chart, perhaps even counterproductive. As I said, fault identification is now no longer essential, and in fact it's probably not even possible, because I think you can only anticipate this vanishingly small set of those faults. And it may even be counterproductive, because your desire to try to tell the system how to adapt is probably poorer than its ability is going to be to assess what the situation is and come up with a solution to best meet those operator goals on its own. So that requires new principles for architecting software that can support the needed levels of system complexity and adaptability. And that's really the heart of the talk here, that if we architect the software systems like we have for the past 20 or 30 years, then the verification and validation challenge becomes asymptotically unsolvable, and that you have to architect the software fundamentally differently than we do today. So it's going to be, these systems are going to be increasingly less deterministic, and the software that drives them is going to be focused on this goal-driven, context-aware adaptation. And the challenge then is, how do you take a near infinite state system like that and do verification and validation on a system of that type? I think everyone in this room knows, coming back now to DoD systems, certainly under the new directive, in order to be able to field systems like that, we have to establish what is broadly understood as certifiable trust. That term is not rigorously defined, but it means not just a promise or a statement that, don't worry, we've got this covered. The system will operate the way it's supposed to, and you don't need to worry about unintended consequences. I think a lot of the experience, even to date, with these systems have shown that we really don't know how to do that, and we're going to have to be able to prove, whatever that means in this context, we're going to have to be able to prove that these systems warrant this level of trust before they're going to be able to be fielded. By the way, I would argue that in a military, in a warfighting context, our desire as a society to achieve that level of safety and security through certifiable trust in these kinds of systems, that puts a tremendous burden on ourselves. As I argued at the beginning, or stated at the beginning, I contend that we can engineer systems today that could leverage high levels of autonomy and adaptability. What we won't field them because we can't do the trust issue yet. There are potential adversaries who may not have, either for cultural reasons or reasons of warfighting advantage, they may not impose that requirement on themselves, and as a consequence may be perfectly willing to field systems that are very, very capable, maybe more so than our own, and can do so because they don't impose that trust burden on them. So I think that's a new kind of warfighting asymmetry that we're going to have to address here. This chart's a bit hard for you to read, but the main point is at the top left is a kind of a historical walk through the number of equivalent software lines of code, starting with the F4 system at the top and going through the the F22, which is about 2.5 million ESLOCs. The Android operating system on smartphones, about 12 million lines of code. The F-35, about 18 million lines of code. And by the way, if you go out and look at a BMW, there's over 80 million lines of code in that. Now, it surprises a lot of people that that's more than what's in the F-35. But keep in mind that the BMW goes out and buys subsystems from independent suppliers who have their own subsystem software, so it's not nearly as tightly integrated as is a platform like the F-35. At the top right is a walk through on the horizontal direction from very simple, traditionally engineered systems through increasing levels of autonomy, complex, leading all the way on the right-hand side to complex adaptive systems. And it characterizes the adaptability, the control architecture, again, the number of lines of code, the structure on which a system like that is engineered, and then finally our ability to certify systems like that. And on the bottom you see, as we go through today's simple engineered systems which we know how to validate, they're going to be semi-validated, perhaps weakly validated, and then for these highly capable systems it's not entirely clear how we're going to go about doing that. One of the keys here is that even in mission critical systems where a tremendous amount of resources is put into the software engineering, it turns out that if you look across a number of these most critical systems, there's about 4 to 6 errors per 1,000 lines of code on average in most software, and you can get it down to about 1 or maybe 10 to the minus 1 errors per 1,000 lines of code in these very highly engineered systems. That means if you go back and look at the F-35 software, there's of the order of 1,800 errors in its operational flight program. The errors here in the software are not traditional coding errors. There may be those, but those are fairly easy to detect. They are more errors that arise in the logic of the autonomous adaptivity that the system can take on. And those are much, much more difficult for us to be able to find. So there are formal methods, of course, and I think most of us understand that as the system complexity grows very rapidly, these formal methods, based on various abstractions and model-based checking, they don't tend to extend to those kinds of systems very well. One approach is to say, I'm not actually going to try to V&V the autonomous adaptable software that drives the system, because that's just too hard today, and it is hard today. I'm going to abandon that, and I'm going to try to do what amounts to runtime V&V, define a set of acceptable operating limits, and then when the system tries to go outside those limits, I'm just going to turn off the smart controller, default to some very low-level, simple controller, but a controller that I can V&V because it is so simple. And then once I've driven the system back into an acceptable operating state, then I'm going to switch back to the smart controller. So not really solving the problem, but if you will, sidestepping the problem. I would argue that actually, if you think about it, doesn't work. And the diagram on the right is meant to kind of show why that really doesn't work. So in the gray here, what we're showing is the range of actual possible system performance. And as we've argued here, that is fundamentally unknowable. We cannot a priori determine what the full range of states and operating modes is that a system like this can go into. So that's a cloud. It has no well-defined edges. In the green at the center is what I describe as the system developer's intent. And I would contend that even that is imprecise, because the whole idea behind a complex adaptive system is that we are no longer trying to tell the system everything that we want to let it do. We want to let it be able to adapt. That's the whole attraction of these kinds of systems. So while the system developer may be able to state some aspects of what acceptable performance is, that is fundamentally imprecise. And then I would go further in red, the limits of acceptable performance, those are perceived limits, and they're squishy in and of their own. So depending on what the state of urgency is, those boundaries themselves are not fully firm. So as a consequence, the system validation, even with this kind of a runtime approach that seeks to sidestep the problem, is based on assessing the acceptability of performance based on unknown or ill-defined criteria. Now, on this chart, I'm just going to make 1 or 2 points here, because we're going to get into how you would architect the software system to be able to do real verification and validation, not just runtime V&V. And so one approach here is to begin to break the software down, and we already do this in most engineered systems, break it down into a set of sub-functions, and then have the individual software components for those sub-functions, at least at that level, be V&V'd by traditional or by small departures from traditional methods. And then the challenge becomes, as you integrate these systems together, how do you ensure that these simple models for the subsystem performance are going to lead to this higher level system performance that still enables the emergent behavior that we want to achieve, but can allow us to understand what the range of that behavior is. And so here we draw on, or at least I would contend we draw on advances in network science over the past couple of decades, where we've learned that if you go at the diagram at the bottom right, simple systems have a few number of subsystems, and those would correspond in a network diagram to a few node system, like what's shown on the left side there. A complex adaptive system is going to increasingly correspond to a many node system where there are large numbers of interactions among the individual component nodes. What we've learned from network science, or one of the things we've learned, is that if you have a few node system, then the models, the fidelity of the individual node models becomes central to the fidelity of the overall system model. When you go to the right on these many node systems, you can actually have fairly weak fidelity in the individual node models, but because the system dynamics is driven now increasingly by the interactions, by the links in the network graph, rather than by the dynamics of the nodes, it is that set of links that drives the overall system performance. And because of that, you can get away with very simple models of the individual nodes, the individual subsystems, and still have an accurate representation, not a perfect, but an accurate representation of what the high-level system behavior looks like. So if we're going to take this network science-based approach to architecting the software, then if you look at the top right, there are a couple of ways that you could try to do this. Today, we start out with developing the individual component submodels without much concern about the overall architecture and what the topology of that overall architecture is going to be. So we often get very distributed structures. If you go back to network science and you think about centrality and betweenness and concepts like that, that can quantify some fundamental aspects of the topology of that system architecture. At the top right, on the right-hand side of that diagram, is a notional sketch of an equivalent system, the same nodes, but now architected in a way that has a more hierarchical structure to it, and that as a result of that structure allows you to be able to do the V&V at a series of successive abstractions, where at each level in that hierarchy, the models may be simpler or maybe even crude representations of the actual performance at that level. But as we've just argued, it's the interactions among those components that are more important, and we may be able to get away with relatively simple subcomponent models. I would contend that it is not the fidelity of the individual node models that drives our ability to V&V a system with this approach. Rather, I would contend that it is the near infinite state system problem. The fact that as we now go and operate the system under a wide range of conditions over which it's going to operate, because it's a near infinite state system, we're only going to be able to test an exceedingly small subset, in fact, a vanishingly small subset of all the possible sample space that system can operate over. And as a consequence, we can use all kinds of smart approaches, moving away from factorial methods and going to response surface methods and other approaches that allow us to make the most use of the small sample of test cases that we can do, but it fundamentally leads to a high level of uncertainty that the system is going to stay within acceptable bounds of performance. And then if you go to the bottom right, as these systems are very nonlinear, that response surface may not be as simple as it is in the top diagram, but it may have very, very poor characteristics that allow this fundamentally small subset of the sample space to be perhaps very poorly representative of the overall system behavior. So it is that near infinite state system problem that I argue is the largest single challenge. I'd go beyond that one more step now, and not to muddy the waters more, but we've said that a fundamental piece of this is that these systems have to be able to self-learn as they operate. And one of the ways they can do that is through non-deterministic stochastic dither in their operations, so that they're constantly experimenting, trying to, even as they operate, learn more about what good control of a system like that looks like. And that induces another component or another dimension to the V&V challenge, because now the confidence level is something that can only be stated in a probabilistic sense. Now, a key question is, what is the confidence level that we have to show to be able to establish certifiable trust in a complex adaptive system like this? And if we go back to what I would call Apollo-era low-dimensional finite state systems, we set that demand at near 100%, 99.99, however many nines you want. Because we literally could put the system into all possible states, test them deterministically, and assess how the system responds. Today, I would say most people still believe that we need to be able to certify that to in excess of 99% criteria. I would argue that if we're going to draw the advantages of complex adaptive systems, we're going to have some way of backing away from that 99.99% mindset. And exactly what that means is something that the community has to figure out. It doesn't mean accepting risk willy-nilly, but if we're going to insist on 99.99 whatever, you are not going to have the complex adaptive systems that your adversary may very well have. The last bullet, we have as a society this, not one life should be lost mentality that's, very virtuous. And, but that mentality may be fundamentally inconsistent with these kinds of systems. And we accept risk in other ways as a normal part of the engineering world. And I think we need to extend that into this system as well. Not blind risk, but something that's much more refined than that. Okay, as I think all of you know, DoD has a number of stated science and technology priorities that were articulated in a memo from then Secretary Gates back in April 2011. I've listed those 7 priorities on the right here. They're often affectionately known as the Magnificent Seven. At least 3 of those are central to this whole idea of complex adaptive systems and how you do V&V on them. The data decisions, the engineered resilience systems, and the role of autonomy. And ASD+R&E, as you know, has the Systems 2020 initiative that also has a focus on things that will support the development of these complex adaptive systems. Those 4 thrust areas are shown in red. Certainly number 3, the capability on demand, directly addresses V&V of adaptation in systems like this, both self-adaptive systems and field adaptive systems. So I would argue that this is a community-wide challenge. I've listed here some of the main organizations that are involved in having the engineering community continue to move away, but increasingly rapidly move away from these simple engineered systems as we've defined them here in the last few minutes, towards these highly adaptable, complex adaptive systems with all of the advantages that they can bring, benefits for society at large, but with a whole new set of risks and a poor set of tools that we have, or more precisely don't have, at our disposal today to be able to manage those risks on behalf of society. I've argued here that this requires a shift in the fault management paradigm, the traditional fault management paradigm, to a whole new way of looking at it, throwing out the traditional model of normal operations punctuated by discrete and, importantly, anticipatable fault modes, to a kind of an architecture where the system is constantly adjusting to its current state. And whether you want to call those faults or not, it's just another driver that causes it to move into that system. Some of the issues that I've talked about here, the stochastic self-learning, the small sample problem, the fundamental small sample problem, all of these are ones that we're going to have to come up with as a community ways of addressing. And I would argue, as my get off the stage point here, that it is fundamentally driven by architecture of the software that is resident in these systems, that controls these systems. Unless we start architecting or even conceiving the software from the beginning so that it is more V&V-able, I don't think we're going to be able to achieve this certifiable trust that's required. Okay, my promise to you was I'd leave a few minutes here for questions. So with that, I'll stop here. If there are any questions, I'd be more than happy to try to address them as best as I can. Thanks for your attention. Yeah, over here. So it's an interesting point you make, and I think it's a very important one. At some level, there are two challenges here. One is for the engineering community that's in place today and that is working increasingly so on systems like this, and what tools can they have. But you raise a really important point, and that is that, what's the next generation of engineers whose entire careers, I think, are going to be faced, or at least for very many of them, faced with systems like this, and what do you have to teach them to be able to do that? I think, first of all, an awareness of the challenges, and to the extent you agree or disagree with my points here today, the fact that it is ultimately a software engineering challenge, right? We know how to build systems like this. We just don't know how to architect them to be able to be V&Vable. Secondly, I think most students have a poor understanding of risk and the fundamental probability basis of risk, and that is central to this. I think until engineers, and we've been trying to move engineers in universities more towards an understanding of statistics and probabilistic methods and so forth. But I think having them understand that fully deterministic systems of the type that we have traditionally taught is a waning paradigm, and that systems that are fundamentally probabilistic in their operation is essentially where the future lies. But it's a huge challenge, and you mentioned a whole set of the boundary conditions that are placed on that part of the community that's trying to teach these people. It's a tough but exciting challenge. Any other questions? All right, I thank you for your attention. Enjoy the day 3 of the Aerospace Sciences meeting.